Hello, everyone. Welcome. Thank you so much for joining us today. We're really glad to have you all and excited for this presentation. So while we're letting everybody trickle in, I'm going to run through some quick introductions and housekeeping items. So my name's Kayla. I'm here representing the Acelab team, and we have Leah and Hugh here from Elemex. So before I pass it over to them, I'm going to go ahead and pull up Acelab and walk you guys through their page. So in just a moment, you should be able to see my screen. All right, so here we are in Acelab. If you're not already familiar, a really great way to get started here is using the search bar at the top of the screen. So you can filter for product, manufacturer, resources, or definitely check out our new AI search. It's a really great new functionality that we have. But here in this case, we're on LMX's page. Got some really great content here for you. We've got some contact information, as well as their products here for you to explore. So you can click into any one of these pages to get more information. We've got some great downloadables, things like that. You can also actually save it to your firm library right here. That way you'll have it for future reference. And we have some case studies as well. So I'll drop a link to their page here in the chat. So check that out when you have a moment. Couple other things to make note of. This is an AIA-approved presentation, so we already collected your numbers upon registration, but if you're worried that we didn't get your number for some reason, I'm going to drop a form in the chat as well. You can fill that out to make sure that you get credit for today's session. We will also be doing Q&A at the very end, so if you have any questions throughout the presentation, feel free to drop them in that Q&A button at the bottom of your screen. We'll get to as many as we can at the very end of the presentation. You'll also see a webinar poll pop up on your screen about 3/4 of the way through the presentation. That there is an optional poll, so if you're not interested in getting any kind of follow-up information, just click the X, it'll go away. However, if you are looking to get connected with the LMX team after the webinar, fill out that poll with any specific information you'd like to request or any project details you may have. We will connect you directly with the LMX team via an Acelab conversation. So you'll get an email notification when that conversation is created within a few days after the webinar. So keep an eye out for that. And lastly, we will also have a post-webinar survey for you. So we really appreciate your feedback on this presentation. So feel free to leave anything like there at the very end. So with that being said, Hugh, I'll go ahead and pass it over to you to get us started.
Fantastic. Thank you, Kayla. So, hi, everybody. My name is Hugh Lowry. I'm the Technical Engineering and Sales Manager over here at Elemex. And today we're going to be going over solar facades, understanding building integrated photovoltaics, and pressure equalized rain screens. So without further ado, we'll hop right into that. This program is registered with the AIA, as Kayla just mentioned, so we're not going to spend too much time on this, but as you guys know, you can get certification for this course. This presentation is copyrighted by U.S. and international copyright laws, so please don't reproduce it without any permission from us. Okay, so learning objectives. Quickly go over these. We're going to discuss the benefits of environmental benefits, of building integrated photovoltaics. We're then going to go into the benefits of photovoltaic facades for the environment and demonstrate how BIPV facade systems can contribute to LEED certification goals for architects and owners. We're going to go through the components and possible attachment methodologies available for successful design and installation of a BIP facade system. We're also going to discuss the applicable standards and codes that are associated with modern BIPV facades and explain the advantages of specifying a pressure equalized rain screen system alongside a BIPV facade system. This is registered in Canada as well. See the Canadian Architects Associations there. Okay, so course outline. We're going to provide a basic overview of rain screen technologies that are being used to incorporate building integrated photovoltaics into even the most discriminating design demands. We're going to discuss the important role on-site power generation can play in creating positive positive environmental impacts, contributing to LEED certification goals, and positively impacting costs associated with energy use. We're going to look at the components required to successfully install and operate a BIPV system. We're also going to talk about some of the design consideration architects should be paying attention to in order to maximize the solar capture and system performance. And again, we're going to talk about what codes actually relate to BIPV systems and how can we meet or beat those building codes. And then finally, we're going to discuss the advantages of specifying a solar facade system within a rain screen system as well. Okay, so we're going to start with a basic definition overview of what a BIPV system actually is. We're going to talk about how recent advancements in technology have allowed for BIPV systems to be incorporated into building facades using rain screen mounting principles. We're going to look at the benefits of BIPV system, benefits for the owner, the occupant, the manager, and the environment. We're going to talk about environmental benefits, but also health, safety, and wellness benefits for the occupants of the building. We're also going to look at, with those environmental benefits, how we're reducing greenhouse gas emissions and how that impacts climate change. And then finally, we're going to talk about lead points and how they relate to the system. So what is a BIPV system? I'm going to use this acronym quite a bit throughout this presentation. It stands for Building Integrated Photovoltaic System. So BIPV systems basically are different from applied photovoltaic systems, a BAPV system, with the fact that BIPV systems have a functional role in the building envelope. So it's not only serving as an energy generator, it's also serving as the material on the outside of the building as well. There's a key differentiation here where like our product and BIPV specifically is that skin of the building. You might see applied photovoltaic solutions like rooftop-based solutions, or even on a facade system, you might see an applied solution, being a second skin, maybe in front of an ACM panel or something similar. But BIPV specifically, the solar panel is acting as the skin of the building, is crucial to the building envelope. If you remove the photovoltaics, you would see an incomplete building. So what should you be looking at before you design a BIPV system? So first, you're going to have to understand the energy needs of the building itself. You're going to have to understand, how much energy is that building using? What kind of voltage is it at? Can it, successfully incorporate and accommodate a BIPV system? You have to look at the owner and occupant needs. What's the primary goal of the owner with this system? Are they looking for return on investment? Are they looking for environmental impacts? Are they looking for sustainability impacts? You have to look at the building's applicability. Like what kind of system makes the most sense there? Is it a building where a rain screen makes sense? Does a curtain wall make sense? Things of that nature. And then finally, you really have to be sure you're working with experienced professionals within the field. This is a relatively new niche field, so you have to make sure the design, installation, and maintenance of the system is being performed by people that have experience with these types of systems. So two basic photovoltaic technologies that we use in BIPV systems. There's thick crystalline products, so solar cells made from crystalline silicone. These would be your traditional panels that you would see, on a ground-mounted solution or a rooftop-based solution. They kind of resemble a grid, if you will, or a checkerboard of some nature. They have a thicker active layer in the middle that's made of that crystalline silicone. There's also thin film products. So thin film products are basically a thinner active layer that's vacuum deposited onto a glass substrate. You can actually see one in the background of this slide right there. I like to point that out. So a little bit different than what you would typically see from a PV panel itself. A little bit more homogeneous in the look to it, but it comes with a lower efficiency. So two major types of technology. The important thing to note is that the crystalline silicone is more efficient generally, but the thin film product can look a little bit more homogeneous. There's many different types of applications involved with BIPV. So obviously you can have a roof application. We've seen lots of those type of applications. Be different than a rooftop array type application. A BIPV application in a rooftop would have to be something that was necessary to the building. So in that case, it could be roof tiles or shingles, things of that nature that are also photovoltaic generating. Windows, pretty straightforward application here. You can basically just replace the glass in any window with a photovoltaic panel. They can be semi-transparent to allow some light through the window while still maximizing solar capture. And then finally, the last one we're here to talk about today is rain screen facades. So getting into rain screens quickly, what actually is a rain screen? So the rain screen can be a bit confusing because at the end of the day, all you're seeing is the exterior cladding. But the rain screen is really the whole system between the exterior cladding and the building substrate. So a good way to think about it, it's the most effective moisture management system that includes the building cladding's exterior wall components. The screen part of the rain screen obviously refers to that outermost layer that you're actually visible on the outside. Other components present within the system is an air gap in between the screen itself and the weather barrier. This has a capillary effect, a drying effect, so air moves upwards vertically in that air gap to promote drying. In short, a rain screen system lets air into the wall structure as a way of keeping rain and water out. So what kind of rain screens are there? There's two main types: drains and back ventilated and pressure equalized rain screen systems. Um, they're both rain screens, but they differ in terms of acceptable water penetration allowed with the rain screen. So pressure equalized rain screen systems tend to be more stringent in their requirements for the allowed a degree of acceptable water penetration. So how do rain screens keep the water out? So there's 4 Ds associated with rain screens. So first and foremost, we have the deflection of the actual veneer itself. So with a rain screen, you are letting air in behind the wall cavity, which reduces the pressure difference across the exterior cladding component. By reducing that pressure, you're basically reducing the amount of deflection that panel is actually going to experience. We also have a drying effect, that air gap that we mentioned behind the panels. Hot air moves up that channel, promoting drying as it moves upwards. We have drainage, which is basically, any water that actually penetrates beyond the paneling system is directed down a drainage channel and out the bottom of the system via flashings. And we also have durability. So by limiting the amount of water that's reaching that weather barrier, we're promoting durability, and also by limiting the deflection of the paneling system, we're also promoting durability in that sense. So we're going to get into drain back ventilated real quick. So they're designed for water entry and exit, and they have an open joint system. You can see in the joint, in the picture to the right, there's obviously an open joint there in the middle of the wall. And I want to point out attention to that because the next slide is going to be a bit different. But the joints are designed to allow both water and air in and out of the system. The ventilation cavities between the basically the screen or the cladding itself, and then the insulation back there. And its job is to help water drain from the interior down vertical channels, as well as promoting airflow to evaporate moisture. You have to have fenestrations in the system to, they'll be flashed and detailed to collect and direct water out of the system. And then finally, we have an air-water barrier at the back of the cavity. So pressure equalized systems. You can see that joint is a little bit different. We have a semi-closed joint in this type of condition. So we are letting air into the system with this condition, but we're limiting the amount of water that's left in that system as compared to an open joint. And that's why pressure equalized rain screen systems are more effective than drain back ventilated rain screen systems. You are still letting enough air into that system that you get the pressure equalization across that paneling, and that's denoted by the high pressure zones of that H in this diagram. But you are having some sort of joint treatment that's basically preventing water from just straight up entering that joint. With the pressure equalized pressure, the high pressure zones on both sides as well, by letting air into that wall cavity and equalizing the pressure, we're also reducing the chance of any water that's sitting in the joint being sucked in as it tries to move to a low pressure zone. So getting into how pressure equalization keeps water out of the building envelope. So all buildings are subject to pressure differences from the wind, basically. Driving winds increase the pressure in front of the panel, and that basically causes the panels to deflect. That pressure difference also causes the building to draw in water from the outside. So if we're looking at the picture on the right there, there's a high pressure zone outside of the panel from driving wind, and there's a low pressure zone inside the panel. And this can be because, maybe that joint isn't open enough to allow airflow through it. So basically what happens in this case is, things like the move from high pressure zones to low pressure zones. So if any water sitting in that joint, it will start to move toward the low pressure zone just naturally. If you have basically some air being let in that cavity and there'd be high pressure behind the panel as well, water won't be sucked through that joints at all. So they do that basically by pressure equalization. They do it by way of compartmentalization and back venting. Any water that finds its way in is reduced, and the residual moisture is returned to the panel's exterior at the drainage plane. So we've covered the basics of rain screens. So let's look at BIPV systems and how rain screens and BIPV can be brought together. Recent advancements in technology have allowed for BIPV systems to be successfully incorporated into building facades using innovative rain screen mounting principles and solutions. BIPV solar facades use PV modules that are either combined with the building during the construction or integrated later, often as a retrofit with the outer surface replacing the old facade. Okay, so common misconceptions of BIPV solar facades. Traditionally, when it went to BIPV, you were limited in the type of offering that you could put on the building just from industry. There weren't colors, there weren't custom sized shapes, they were bulky. They basically had to fit on the building in the size they were manufactured on. They were unattractive, and that is no longer the case. That is now false. New technologies have allowed BIPV to incorporate in the solar facade system with a wide range of products for very innovative design options. Solar technologies can integrate seamlessly and even enhance the building's appearance. Colored panels that have high aesthetic value are now being implemented. into the facade of commercial buildings. Sleek panels can provide a new design element that is worthy of displaying rather than hiding. I'm going to quickly jump into the solar facades benefit, both for the people and the environment. We'll start with the owner, then go to occupant, and then finally finish up with the environment. So solar facades incorporating PV into the structure of the building instead of needing to be mounted in or on other usable spaces like the rooftops. So for that reason, you can free up your rooftop for other value-added amenity spaces. We've done projects, and we'll show you guys one at the end, with the solar facade, basically opening up the rooftop to a patio space. So they were able to use the patio space for entertaining. Had a wet bar, a TV, things of that nature. But they still had a solar system incorporated into the building through the facade. So they're able to free up that rooftop space and have solar on the building, can add a value-added amenity for the ownership. So the benefits of the owner are also shared by the occupants, especially if you're using that rooftop space for, a patio or a community gathering space or a rooftop garden. So that could benefit the occupant as well. The reduction of bulky solar panels can provide better visuals as well, providing the owners and occupants with an improving living environment and improved building aesthetic. And also, understanding solar facades isn't just about the aesthetics or reducing the carbon footprint. There's also health, safety, and wellness benefits that are central to the solar facade success. So there's a lot of fire testing these panels go through, a lot of codes they have to adhere to, and they all help create a durable, safe, and sustainable facade, one that helps support the health and wellness of the building occupants. In terms of benefits to the environment, one of the major benefits of the solar facade is the on-site power generation, which can contribute to the fight to slow climate change. The incorporation of on-site power generation helps lessen the building's dependence on fossil fuels that may be associated with grid-based energy sources. Photovoltaics obviously generate clean energy, which reduces the carbon emissions when compared to the oil-based energy source. So this can be measured in a variety of ways, primarily either by the CO2 of the weight of the CO2 displaced by the solar facade, or the equivalent trees that would need to be planted to have the same carbon displacement. There's been some research using life cycle analysis and building energy simulations to look at operational carbon emissions of BIPV buildings, has shown that BIPV installations can reduce emissions of that building by up to 50% over the lifetime of the building. So potential lead points through solar facade systems. Under lead 4.1, on-site renewable energy can provide up to 5 lead points, which is 12.5% of the way to basic lead certification. In order to get those full 5 lead points, you have to have 40% of the building's electrical usage coming from the photovoltaic system. So a fair amount of design work has to go into making sure that you're covering that 40% of the building's electrical usage. But it's fairly easy to even get just 1 point. With the first category of points basically starts at 2% of the building's electrical usage must come from on-site renewables. So this can be a good solution for the building if you need 1 or 2 more points to get basically over the hump to lead certification. This can be a great solution for that. So there's another technology that recently appeared on the market, and it's one that we feel helps improve both performance and the aesthetics of BIPV facades. And the traditional solar panels have aluminum frames and brackets that always don't fit in with the design of the building necessarily. So frameless panels are now available. Frameless panels are composed of solar cells sandwiched between 2 sheets of glass without frames. And they can be mounted mechanically using bolts through glass or clamps. They can be mounted chemically using adhesives, a variety of mounting techniques. And obviously, when you look at the building, you can see on this photo right here in the background, a frameless panel provides nice, clean, crisp edges at the edge of the panel rather than a bulky frame that goes over the face of the glass. So while the aesthetics of having a frameless panel blend into the facade may be convincing enough, there's actually other advantages to frameless panels. Frameless panels are less susceptible to degradation because glass-on-glass mounting joints are more resistant to expansion and contraction. Due to the lack of metal framing directly attached to the solar panel as well, not isolated from the solar panel, there's less chance of any electrical current leaking out of that panel into the framing system and going to ground. There's also increased fire performance with frameless panels. Because frameless panels are glass on glass in order to maintain their rigidity, when compared to a framed panel, which might have a glass front sheet, but because it has a rigid frame, they're able to get away with a plastic back sheet. And that plastic back sheet may have decreased fire performance when compared to a glass module. So by avoiding the plastic back sheet and sticking to glass on glass construction, it also has improved fire performance as well. So we're going to go into the components of a BIPV solar facade. We'll provide a start to finish plan for architects to help you understand, the benefits of selecting a manufacturer who can support the design and specification process, provide installation, or provide extensive training for a successful installation. We're going to talk about this, required components, how to integrate with existing infrastructure, and mounting options. Also included in this section, we're going to talk about where the system will be located, how you tie into building infrastructure, also to how to improve performance through orientation, and the appropriate attachment methods for each option. Okay, so components for a BIP solar facade. Starting with the obvious, solar panels. Also in this diagram, you're going to see inverters, safety equipment, and basic wiring. So solar panels themselves are the modules that use sunlight and convert that sunlight into energy. Inverters change the DC energy coming from the panel into AC energy usable in the building or to push out to the grid. There's also rapid shutdown equipment that ensures first responders have access to a button or switch that can rapidly de-energize the system. We also have disconnect switches that are put in for safety, and so that's parts of the system could be turned off for maintenance. Also present in this diagram is a combiner box, which basically simplifies a number of inputs to a number of outputs. They can be used on the AC or DC side, but their basic function is to simplify inputs to outputs. We're going from 2 to 1 in this case. And then finally, there's miscellaneous components like wiring and fuses. So necessary to the solar facade system are the solar panels themselves. You mentioned these photovoltaic cells use sunlight as a source of energy to generate direct current electricity. So also expanding on the inverter, you can see one inverter in the background right there. As a reminder, an inverter is what takes the DC energy from the solar panel itself and transfers it to AC energy, which is used in the building itself or fed into the electrical grid. The inverter is also kind of the brains of the system, if you will. It monitors things like it does grid detection, it does anti-aliasing protection, it monitors the solar array itself and talks to the internet to push that data out to a monitoring portal. The inverter is the brains of the system for sure. There's also rapid shutdown equipment. So that was introduced in the 2014 National Electrical Code to offer a simple way for firefighters and other first responders to de-energize the solar system in the event of a fire or emergency response. The rapid shutdown is necessary because even if the inverter is turned off, basically there might be still some DC circuits within the system that are live or being energized by the solar panel system themselves. The rapid shutdown is also necessary because often when first responders arrive to an emergency operation, one of the actions they may take will be shutting off power to that building from the grid. If the solar system is backfeeding that building and they're not expecting it, that could be hazardous. So they want the ability to shut off power to the grid and make sure everything on site is de-energized. It's another example of a BIPV component that protects the safety of the people occupying the building. We also have disconnect switches, which I mentioned earlier are put in for safety, and they can be turned off for maintenance of certain parts of the system. You're going to see a disconnect switch on the far right of this picture there. I should mention as well, the photovoltaic rapid shutdown system is that box to the left of the inverter. The inverter is in the middle. And then finally, there's wiring and fuses to complete the system as well. Okay, so we talked about the basic components, the basic system. You need to know how these components are attached and integrated into the building. So complete BIPV system includes PV modules with specific characteristics developed for building integration. Because they're being integrated in design, they will have other appealing features that combine well with other building materials. We also require a mounting system to attach the PV modules on the building facade. And finally, we require an energy system, which will link the PV modules to the building and the grid itself to maximize the use and generation of the solar panels themselves. You can see an example of a photovoltaic rapid shutdown initiator in the background of the system too. So you see that little red thing kind of just to the right of that box. So that is the button that firefighters would hit in order to activate the rapid shutdown on this system. Below that, you can see another example of a disconnect switch. In this case, the disconnect switch has a window. It's because it's an exterior disconnect switch, and it's just one that the firefighters could technically throw. We want to make sure that you're able to see into the exterior disconnect to make sure those contactors are disconnected. So that's why that one has a window. So there's a few different ways to mount solar facades. You can have a curtain wall, you can have a spandrel panel, structural glazing, or a pressure equalized rain screen. Curtain wall is fairly straightforward. It's aluminum framed wall containing infills of glass, metal panels, or thin stone. Obviously, the solar panel could go in place of that glass, metal, or thin stone. It's important to note that you can also get solar panels in IGUs for use in a curtain wall system. So they can have insulating properties. Spandrel panels provide another mounting option. There's also structural glazing systems. It might be similar to a curtain wall system, but maybe it's bonded in slightly different methodology. And finally, there's pressure equalized rain screen systems, that can be employed to support a solar facade. Rain screens are ideal for water management, like we talked about earlier, and they incorporate other features like insulation. In these systems, rain screens specifically, the panels either chemically or mechanically fasten to a rain screen support structure. We'll quickly go over the design considerations, and there's a slide for each one of these ones, so I'm not going to spend too long on this one, but we'll start with size. So larger format solar panels can generate more power because of their largest surface area. The more solar cells working together, the more panel of power can create. A typical residential solar panel is about 65 by 39 inches, and in commercial operations, you might find larger panels that approach 79 by 49 inches. You are seeing solar panels get larger over time. This is generally because most manufacturers want to promote, they have the best wattage for their product, and the larger the panel they make, the more wattage they can kind of fit into their product. So in general, you will see wattages and sizes going up over time. Irradiance is also another key design factor. So irradiance is basically the power per unit area received from the sun. And, it's going to affect how much sun is basically falling on that panel, and therefore in turn how much power that the panel is able to generate from the sun falling on it. Solar panels are able to convert both direct and diffuse radiation to energy to electricity, but direct is most efficient. And we'll talk about when you would have both in a second here. Efficiencies of panels are going up over time as well. So going back to that standard size we talked about earlier, 65 by 39 inch. In 1954, it produced about 20 watts, or about 6% efficient. 2012, obviously 50 years later, we're producing closer to 200 watts, and we're 15% efficient. In 2020, produced about 320 watts, and we're 18.7% efficient. If I had to add another, basically little note to the slide, we'd say in 2025, we're producing about 400 watts and we're approaching 21% efficient. So there are still advances in the technology being made to this day, changes in cell size, half cells, things of that nature, different types of technologies. These panels are still getting efficient, more efficient, I should say. The wattages still are increasing for a common size. And as we see that efficiency increase and that power levels increase, it only increases the viability of this product as well. Orientation is also very, very important to the solar facade itself. We're in the northern hemisphere, so the most sun comes from the south. So the south wall is definitely going to be the best. East and west walls can also be pretty good, maybe 70 to 80% of the production of a south wall. North walls are fairly terrible in the northern hemisphere. All you're getting at that point is that diffuse radiation that we talked about earlier. So you're not getting any direct sunlight. You're actually getting sunlight that's bouncing off molecules in the air and then somehow hitting that wall on the north side. And like I said, that's about 30% of the power that you would get from the south wall. So takeaway here is not worth doing the north wall. Could be worth doing the east and west wall, depending on orientation of the building, but you really should be looking at your south wall in order to maximize solar capture in the northern hemisphere. Another thing that's mentioned with orientation is typically you would want your solar panel to be entirely perpendicular to the sun rays for maximum generation. So in the northern hemisphere, that's somewhere, around 30 degrees. If it was, we're obviously stuck with a 90-degree tilt because we're trying to apply our solution to facades. So that has to be consideration as well. You can have things like sunshades and, making the sill panel for windows, a solar panel that can help direct the panel back more towards an ideal angle. But typically we are stuck to a 90-degree tilt perpendicular from the ground, and we don't generally see motorized or articulating systems involved in BIPV as well. So they tend to be fixed or stationary. So next, we're going to look at specific standards and codes that apply to BIPV facades with a quick dive into IEC 61730. So what is IEC 61730? It's the first international harmonized standard for PV modules. In the past, each jurisdiction had their own certification program. This became an issue when you're manufacturing in one jurisdiction and supplying to another jurisdiction. So that could, create confusion. If the certifications don't line up, it could lead to callbacks, fines, safety issues, reinstallation, things that we don't want. So IEC 61730 was the attempt to harmonize and standard solar panel certification across the globe. And without it, you basically can't get off the ground. You can't install a solar panel in North America without this certification. It's a very important one. It's broken up into 2 parts. So part 1 incorporates the language from UL 1703 into the harmonized standard. So UL 1703 was the North American standard for flat plate photovoltaic modules and panels. That's where our language and our jurisdiction comes into this global harmonized standard. So this standard ensures compliance to all North American electrical codes with additional focus on BIPV and rooftop applications. It covers adherence to the National Electrical Code, the NFPA 70, and which is the National Fire Prevention Code as well, or model building codes. It contains some fire testing relevant to rooftop applications, such as spread of flame and burning brand testing. It's worth noting it doesn't cover any facade applications specifically, and we'll talk about where we fit into that in just a second here. So part 2 of the IEC 61730 provides the safety testing requirements to verify which materials are being used, how they're integrated in the PV module specific design, and how that design is produced into a finished module as well. And I promise we come back to fire testing. So because we straddle both the electrical world and the building world, we have to adhere to both electrical codes and building codes. So our fire testing that we feel is most relevant is actually contained within the national building codes, Canada and the States. So that'd be NFPA 285 in the States and CAN ULC S134 in Canada. So it is important that both of those standards do apply to these facades as well, because they do straddle the building world and the electrical world. Okay, so now we're going to talk about, solar facades and pressure equalized rain screens together. We kind of talked about them separately, but there are specific advantages to specifying a solar facade in a pressure equalized rain screen. So just quickly going over pressure equalized rain screens once more. So we learned that pressure equalized rain screens basically work to limit how much water actually gets past the exterior cladding of the building in the first place through joint design. And then it also equalizes the pressure across that cladding by allowing some air in to reduce outside pressure forces and stop water from being drawn into a pressure differential as well. So pressure from the wind obviously sends rainwater into a building's wall system. Pressure equalized rain screens help mitigate this problem by reducing that pressure differential across the cladding by way of compartmentalization and backventing. Any incidental water that does enter the system is directed down the drainage plane and out the bottom via flashings. So why are they so ideal for BIPV applications? Okay, so we talked about deflection quite a bit. I mentioned the pressure differential across the panels, I think 5 times at this point. That is extremely important for solar panels. If solar panels bend too much, the actual active layer itself can undergo significant stress, which can cause microcracking within that active layer. If there's microcracking within that active layer of the solar cell, it's basically going to reduce the electrical efficiency of that cell itself. So it's really in your best interest to prevent these panels from deflecting too much. They're obviously also made of glass, which is quite a brittle material. So we also want to reduce deflection for that point. But it's important to note that if these panels go through undue deflection, it can actually affect the electrical generation properties of the panels. We want to limit that deflection as much as possible. And we do that through the pressure equalization. Rain screen systems are also very ideal at managing water. You're working to limit the amount of water that penetrates in the first place through joint design, as we mentioned, and then you're also directing all of that water down a drainage plane and out the bottom of the system as well. This is an electrical system, and we all know that electricity and water don't play super nice together. So aggressive and durable water management defense really helps the longevity of the electrical system as well. So we're quickly going to go into a case study on this guy right now, and this is going to be on our first project. You've seen a lot of title slides in the background of these projects, and it's all basically been this first project that we did. We prepared this presentation a number of years ago, and it's mainly focused around this project. We do have some more project examples that we'll share with you post presentation as well. So this is located in London, Ontario, in Canada. It embodies cutting-edge design and construction. It's a world-leading, multifaceted approach to this building. It was completed for Ellis Don. Ellis Don is a large construction company up here in Canada. It completes about $5 billion worth of contracts annually in every market sector across the globe. We were lucky enough that their head office, or their first office, their head office is in Toronto now, but their first office was right around the corner from a manufacturing facility in London, Ontario. So we were able to do a project right in our backyard, which was fantastic. There's a couple of different features of this one. So we started with the Cambrian black granite along the base level. This was primarily because this is a parking lot. So we wanted to make sure we started with material that was robust in the event there's going to be snow removal operations. We didn't want any damage occurring to that bottom layer of panels. So we wanted to use a very durable material. It's worth mentioning that there is like a stanchion or something right basically off of this wall. So the only damage you would get would be from hand shoveling. So we won't be able to protect obviously from a full-on plowing truck, but you will be able to protect against damage from a hand shovel for sure with that type of granite. There's also black aluminum composite materials in this. That's what you're seeing kind of right front and center in this photo. And then finally, there's thin film cadmium telluride solar technology. So there's about 1,300 square feet on this project itself. We were limited to one size when we did this project. That's no longer the case, but the project size in this one was a 24 by 48 inch panel, about 2 feet by 4 feet. It had DC wattage of 18 kilowatts and an AC output of 15 kilowatts. We didn't mention this previously, but I will mention this now. It's important to note that your DC wattage should always be higher than your AC wattage on a project. And that's basically because the DC wattage represents the theoretical maximum that the solar panels could be producing at any given point in time. And the AC wattage represents basically the output of the inverter. So we want to give the inverter the ability to output its maximum power level. So we overbuild the amount of panels we actually need to reach that, because we operate on the assumption that not every panel is going to be generating in ideal circumstances throughout the day. There's south and east facing panels on this wall as well. In the first year, this facade will generate approximately 17,500 kilowatt hours. We're going to displace about 8.75 tons of CO2, and that's equivalent to 225 medium growth coniferous trees. I also love this slide because it kind of showcases the importance of having multiple products on the same facade. So you can see the solar panel up there to the top right. Key thing to note about solar panels right now is that they're made of tempered glass. You're not able to miter them or return them. So you need to basically think about a material that's going to surround, accommodate, and complement the solar material itself. So what you're seeing in this picture, and what I'm alluding to, is the fact that it'd be really hard to go around the corner with the solar panel alone because you're not able to miter it into a nice, neat corner. What you can see here on the bottom is that Cambrian black granite mitered to a nice, neat corner. Right above that, you can see the ACM that is back route and bent into place. So both of those materials allow you to finish off that corner very nicely. So they are great filler materials to help accommodate building features that solar panels can't accomplish. In terms of economical benefit, when we look at the economical benefit for the solar facade itself, we're trying to separate basically sunk costs associated with putting a facade up itself, along with the premium that the solar panel costs. And we price that premium as the real cost of the energy generation of that material. So there's going to be a fixed cost, whether you're putting up ACM, solar, ceramic, whatever it is. We try to separate the premium that solar costs over the other material you're considering, and that's what we try to base the ROI period off of. So why you're seeing two ROI periods in this graph here below. Basically, if you were to install, basically where it crosses the zero line is where the solar becomes cost competitive with the other building material types. So in terms of the value over ceramic or a premium building material, you can reach cost neutrality between the solar system and that premium building material in as little as 9 years. When you're going with a more cost-effective building material like ACM, it might take a little bit longer to reach cost neutrality with the solar system itself. And we're showing in this graph that's about 16 years to reach cost neutrality with a cheaper building product. Mind you, the life cycle of these products are 25 years. And you'll see by the year 25, the solar has a much better economic impact on the project than you would have with the ACM or the ceramic. Solar is the only facade that's going to give you a return on the investment. Okay, we'll go through a brief conclusion. I think then we'll hop into the Q&A section. So we talked about how rain screen technologies blend with BIPV. We talked about why that's such a great marriage. We talked about specifically with deflection and water management. We talked about how BIPV facades affect the environment through on-site generation and reducing reliance on grid sources, which can be associated with carbon and carbon footprints. We also talked about the impact on people and the environment, how that can help the health and wellness of the occupants. We talked briefly about the required components and systems like the inverter and wiring fuses and rapid shutdown, things of that nature. And then finally, we talked about the advantage of pressure equalized rain screens alongside BIPV as well. So that concludes the AIA portion of this presentation. And I think Kayla was going to hop in with some questions now. So I think we'll turn it over to you, Kayla.
Hi. Yeah, thank you, Hugh. That was great. All right. So, looks like we only have one question so far. So, folks, if you have any additional questions, now's a good time to go ahead and drop those in there. Otherwise, we'll get to this question. We can move on to some other slides. But what I have so far, Hugh, someone's asking, what sets a standard size panel at 65 by 39 opposed to the 4896 like drywall, OSB, etc.? Is that European driven?
Well, that's a great question. I actually really like that one. I never had that before. So this is actually a really great answer for this one. So it actually has to do with the cell arrangement. So typically the solar cells themselves, I wish I had one. Actually, I do have one on my desk. Look at that. Typically the solar cells themselves are about 4 to 6 inches by 4 to 6 inches wide. So those sizes that I mentioned before fit in well with either a 60 or 72 cell panel, and those are just basically neat sizes, a neat amount of cells that fit together electrically. So those are basically why those two standard sizes are chosen. I will mention though that we first were just offering standard sizes when we started, kind of our foray into building integrated photovoltaics. We heard resounding feedback from the architecture community that they need design freedom with this type of technology. So we have pushed into more customized size, shapes, and colors. So while there are standard sizes that we offer, we would kind of encourage you to use design freedom and kind of mess around with the sizes that you can use on these projects. And I'll show you some slides of some projects where we have done different custom sizes to kind of show you what I mean by that.
Yeah, that sounds good. Let's go ahead and jump into the slides, and if there's any additional time at the end for additional questions, we can do that there.
Perfect. So this is kind of the fun stuff for me now that we got through the AIA portion. So Elemex, obviously we like our X's here. There's a branding theme that you guys will notice. So Ceramitex basically coordinates our ceramics and natural stones. Solstex is our solar line. And then we have two Illumitex lines with ACM and aluminum plate. Like I mentioned before, they're all based on rain screen principles. So they're all rain screen systems. You'll note the common componentry between systems. This a very similar clip system between the panels. This is by design and on purpose so that you can mix and match panels across your facade with equal sized joints and consistent planes. Like I mentioned before, we're now offering customized sizes and shapes. You'll see that 39 by 67 one up there at the top. So that's 1,000 by 1,700. And that would be the one that correlates to a 60 cell panel. But we can produce these in customized sizes, as low as 750 by 750 in millimeters and as maximum up to 2 by 4 meters. You can see the color range off there to the right, and custom colors are available, assuming the square footage is large enough as well. The panels themselves are about 9 millimeters thick, but the complete system depth is about 2 inches, and it weighs about 5 pounds per square foot. This is kind of a brief example of the attachment system. So you can see kind of the solar panel itself. You see our subframing, our panel framing behind that, which is what we call the unity system. So that's the common componentry between systems will be contained kind of within that section. Then you also have a thermally broken enviro clip in this diagram alongside an L angle. We are also NFPA 285 compliant and soon to be S134 compliant in early December as well. One thing we didn't mention previously as well is the approach to certification. So we have the IEC 61730 that I mentioned previously. So that is a factory level certification. Typically, you would get that, on one model and one size, and then you would go ahead and mass produce that particular model and that particular size. This became a bit of a challenge for us as we got into customized projects. It became a little economically unwieldy for us to pursue full factory certification on every single custom size panel that we were providing to our projects. So we approached basically our evaluation through what's called a field evaluation. So a field evaluation is very, very handy for custom solutions, as is present basically with BIPV. So basically what the field evaluation involves you basically submitting a bunch of data up front to UL or the appropriate authority. They'll review that data, come up with a testing plan. If they've seen your product quite a few times go through this process, the testing plan might be relying on past testing results, but they'll say, okay, I need to see this, this, and this before I'm going to go ahead with your projects. You complete their testing plan, and then when you ship material to site, they come out to site to verify the materials that you're shipping to site and installing on the project are in accordance with everything you submitted to them for review and are in accordance with the testing plan as well. So that's a unique approach to certification that we do with custom solutions that we feel is very valid as well. Onyx Solar is our solar partner as well, so a lot of user experience and a lot of projects worldwide. Okay, so looking at some of these case studies is very interesting. So this is a building we did in California. So the rain screen facade that you can see is actually on the right there, kind of around the corner. What you're seeing kind of primarily in this photo is the curtain wall system as well. We didn't do the curtain wall system on this project, but we integrated both systems electrically. So there's a curtain wall application on this project and a rain screen application, and they go back to one point of connection within the building. So this one was located in Oceanside, California. It was an energy conscious campus. There's car chargers, hydrogen storage, solar carports, etc. We did the south, east, and west walls in a photovoltaic material. You can see the west wall in front of you there. Those are solar panels above and below that line of windows. And again, I mentioned previously, but we integrated both the curtain wall and the rain screen into one common connection point and one tie-in into the building. So there's a great shot of this building that I personally took, so I'm a little bit proud of. So you have to listen to me brag about this for a minute. But I really like this shot for a number of reasons. First and foremost, it displays the importance of having a surrounding material that complements the solar. So if I'm looking at that staircase right there, basically behind that staircase, we put an ACM product, primarily because there's going to be a lot of shading coming from that staircase. So it didn't really make sense to put solar panels behind it. But secondary reason for that being there had to be penetrations into the building to support that staircase. And obviously penetrations don't work well with tempered glass, but they work great when you have a metal panel. So we're able to seamlessly swap to a metal panel basically where the conditions of the building require it, whether that's a jamb, sill, corner, or, a penetration or behind an obstruction. You can see a little bit more of a penetration example if you kind of drift towards the right. You can see a couple of vents coming out of that wall as well. So everything surrounding those vents is solar itself, but that panel that the vent is penetrating through is a metal panel. This solar facade powered batteries, both hydrogen and electrical within their building information system. And in turn, those batteries then powered the car chargers that you can see outside. So you can say in a way, indirectly, the solar facade was powering the car chargers, which I think is pretty cool as well. So the first year, this facade generated approximately 200,000 kilowatt hours and displaced about 103 tons of CO2, which is equivalent to 2,650 BDM growth coniferous trees. Pretty cool project from our perspective. Worth noting that there's 835 panels in this project. We had two typical sizes. One was the 1,000 millimeters by 1,700 millimeters, and that's everything you can see on the building that looks like a common size beside the top two rows. So about 600 of them came in at that size. There was 200 of them that came in at a size just slightly taller than that. And that's what you can see in the top two rows of the building. You'll see the width is equivalent to the panels beneath it, but the top two rows are a bit taller. So about 800 typical panels in this job of two sizes. And then we had 35 unique shapes to finish off the corners. And that's kind of what you can see on the west wall there. You see basically some smaller panels right as it approaches the corner. And that's kind of the custom sized panels that we fit in there to finish off that facade, matching up with the mullions and so forth, but just showing the power of those custom sized panels. We can also monitor these sites. So this is actually real data from these sites themselves. This data is from March, but you can actually look at how the solar array is producing on a given day. If this was the live portal into the site itself, you could actually see weather data alongside your generation information. So you'd be able to say, okay, why is the middle one like a bit cut off at the start, and why is the last one cut off at the end? There's probably weather events that occurred, on the morning of the 23rd and the afternoon on the 24th that actually affected that generation. A typical generation profile will be something closer to you see on the 22nd. So this site level monitoring can basically give you insight into how your system is performing and weather effects that are also possibly affecting the performance of that system on a given day. You can also get panel level monitoring, which is a further level into this monitoring system. So you can actually see how each individual panel is producing on a given day. So the watt hours you see there on the left is how much power the panel is producing. The optimizer list you see there on the right all correspond to a panel on the project. So you can actually track a panel's individual performance. This can be pretty key when you're looking at panels that may have subpar electrical performance. This would be a key identifier into figuring out which panels aren't performing up to snuff. In the event the panel was damaged, this would give you insight into how the damage was affecting the production of this panel. Very powerful tool to monitor the actual panel by panel production as well. Just going further into this project, so we did a mock-up for this project. We are a full architectural shop, so we do all of our own shop drawings as well. So you can see kind of some of the shop drawings there. I just wanted to kind of jump to this. So this was basically a mock-up that we did on site. And we had to match the color of the solar panel with an ACM panel or a plate panel. So basically, you can see the two color options at the top there. So those were custom color options that we sourced from our supplier in order to match the color option chosen for the solar panel itself. So basically, they went with the one on the left, as I'm sure you could tell. But you can see kind of the seamless nature of the paneling system. The only difference between the bottom 4 panels, which are the solar panel, and the top 2, which are metal, are basically the finish. Obviously, one's still a painted metal panel, one's still made of glass. So there's going to be a slight difference in the matte to glossy ratio of the finishes, but the color is pretty much bang on between material types. Show you an example of the wiring as it went up that wall. So these optimizers are the things on the back side of the panel that actually monitor each panel's performance. They also are part of a rapid shutdown system that we employed on this project. So they actually, I mentioned earlier that the firefighters would trip a switch or a button of some sort, and basically these little devices would shut down the power coming from the panel at each device behind the panel. But they also are how the panels are wired together. So each panel is wired into the optimizer, and then the optimizers are wired together back to the inverter. Without getting too technical here, it's important to note that these devices are important to the rapid shutdown solution, are mounted behind the panel itself in the air gap, and contain the wiring that's necessary to wire panel to panel. And this is kind of concept to completion on this job. You can see kind of the original architect's drawings to the left there, and a little bit of the curtain wall system to the right there. So I mentioned before that the project I spoke of was 835 panels, about 800 of which were typical and 35 were unique. The project I'm about to show you right now is the exact opposite. It was about 120 panels, and I believe there was 45 or 50 unique shapes. So a little bit more of a challenging job, I would say, a little bit more attention to detail and dimensions necessary on this particular job. And it came with its own challenges as well that we managed to accomplish. So this was the National Association of Realtors in Washington, D.C. And this actually project, I think, is really cool because it kind of exemplifies that point that I made earlier about the owners and occupants getting value out of the amenity, out of the rooftop space. You know, it actually is true, and it actually can happen. So this was a rooftop space that they wanted to keep open for a patio, for a wet bar, for a TV. They wanted the ability to bring clients up here, kind of showcase how green they are, showcase the views of Washington, but they wanted to have some sort of sustainable aspect on this rooftop. So they went ahead and clouded all 4 walls of the mechanical penthouse in order to promote a sustainable kind of rooftop space while still leaving areas that are, available for that kind of entertainment operations. So we integrated Solstex, with the doors, with a wet bar, with louvers and a TV. We did all 4 walls. Very in-depth project with a lot of custom-sized panels. You can see actually a door being clad right here in this photograph. You can see the Capitol in the background. In the first year, this project would generate about 9,800 kilowatt hours, displace about 5 tons of CO2, and be equivalent to 125 medium growth coniferous trees. So a little bit smaller of a project than the one we talked about in California. But like I mentioned before, a lot more attention to detail, a lot more unique panel sizes, and a lot more integration with this one as well. We had the panel level monitoring on this one. But you can see that wet bar going into place. That's the panels being put up by the United General Foreman right there as well. You can see the color chosen for this project was a dark blue. This is then a shot of those panels, the clip system that you can see attached to the rail. Another cool shot of those panels as they went up. And then this is what I mean kind of by unique sizes and our ability to customize here. So this wet bar actually changed shape and size halfway through the building project. As we all know, building dimensions can change, during construction. That panel that you see kind of put in place there, that's a different color. That's actually an ACM panel. And that's because we had to reorder the solar panel based on the dimensions of the wet bar changing. So we were able to provide an ACM panel that we were able to put up in place while we waited for the lead time associated with the solar panel. I think that's valuable to point out because it allowed them to complete the building enclosure on schedule, even though we had a back order due to a site dimension change. And it also just kind of demonstrates the interchangeable nature of these systems. We truly do build everything off the same platform. You truly can put one panel in place for another. So once you learn how the solar system kind of goes up and goes together, you basically learn all of the systems. And that's our concept to completion shot of this project. And then quickly, I'm just going to use a couple more minutes here. I know you guys have listened to me talk quite a bit, unless there's any questions that popped up, Kayla, but unless you stop me, I'll just keep going because I want to get through this next little section. So we also propose, we also do solar generation proposals as well. So knowing that this is kind of a niche market and a little bit newer of technology, we like to provide as much information and design guidance upfront as possible. So one of the things that we do is this solar generation proposal. We'll put together a number of metrics that basically can help you make a decision or help the owner make a decision about whether this product is right for their building. So we'll start with, a model of some sort, whether it's a Revit model or an architectural model. We can do takeoffs from there, figure out how much solar can actually fit on the building. Excuse me. We can then run something of a solar heat map where you can actually take the buildings, all surrounding buildings in the area as well, run an analysis on how much energy is actually falling on each face of the building, taking into account, buildings that surround the building that may cause shading, things of that nature. You can see in this one that basically this yellow face here is very hot. You can see the green is fairly hot as well, but then as we get lower on the building towards the lower levels, it gets a bit worse. You get a bit darker, and that's primarily just due to shading from the surrounding buildings as well. So very powerful tool. It's very accurate in predicting the generation of the system by looking at the building as a whole and how much energy is going to fall onto it. We'll also outline some basic information like the color selection, how the attachment system works, what a typical electrical system looks like. We'll go into your project facts, like the amount of area utilized, the size of the project, what you can expect in the first year in both generation and return, what you can expect over 25 years in terms of generation and return, some quick financials on the project so you can understand how much this is going to cost you and what your rate of return looks like. We'll also put together generation profiles by month so you can see if you're going to consume the power in the month that it's being generated. You can compare that to the building's electrical usage and see if you can actually consume the power that the solar array is going to generate. We do that both for each wall individually and the project as a whole. And then we also break out the financial model for the project as well. So the financial modeling can be as low, as 8 to 9 years if everything kind of breaks the right way, as it did with this project. And then finally, we'll talk about any government incentives that are available in the region as well. So we'll do all this work free of charge with just a drawing set or a Revit model to give architects, designers, owners a great picture into what they could do with their building and what it could look like for them so they can evaluate if this type of technology is meant for them or not. I think that was the end of my spiel there, Kayla. Thank you.
Yeah, that was really great. And we have some time for just a few more questions that have come in. So I'll jump into these. All right. What is the lifespan of these panels? At the end of their life, does the owner need to follow costly disposal or recycling requirements?
So the lifespan of the panels is 25 years. We also offer a power warranty on those panels for that full 25 years. So the panels are warranted for the lifetime of our warranty, basically for their lifetime. We've also basically, it's been our experience in the past that solar panels aren't necessarily done after 25 years. They just tend to become a bit less electrically efficient. And in the case where they're being used basically in a building application, you could leave them up over 25 years. And basically just see reduced energy coming off those panels. In terms of end of life cycle, I mean, 90% of the panel itself actually is a glass product. The only thing that is not super easy to recycle is the silicone itself in that active layer. We like to use crystalline silicone technology. We have used thin film in the past. Thin film is a lot harder to recycle than the crystalline silicone. So it is possible. 90% of it is glass, which is a fairly easily recyclable material, and the other one is silica based, which is a little bit more challenging, but also recycling, also able to be recycled as well.
Perfect. Thank you. All right. One more question here. Can we have some information on ballistic and wind testing for the PV panels? Does this meet requirement for Miami-Dade hurricane zones?
Yeah, 100%. So we haven't done the 2x4 large missile impact for this product yet. It has been through significant hail testing, but we haven't had impact testing yet. We have been through wind load testing with this in regards to Miami-Dade, and we're in the process of completing that approval. We just didn't know how it was going to stand up to the impact testing itself. So we would recommend putting an impact resistant barrier behind it, but it can stand up to the high wind loads.
Awesome. That's great. Well, I think with just 1 minute left, we can go ahead and wrap it up here. Hugh, would you like to leave us with any final notes or comments?
Honestly, if you guys have any questions about this project or considering a project, please just reach out and let us know. We're a huge source of information, and we're a big company that prides itself on education first, sales second. So we really do like to talk about this type of technology. Really do like to explore what could be possible, for the building and how it could become an energy generating resource and contribute to sustainable goals and things of that nature. We really do believe we're a resource for that. So I'd say reach out with any questions that you guys got, even from an education point of view. We're happy to talk about this type of technology.
Amazing. Well, thank you. Yeah, that was a really great presentation. And folks, if you filled out the poll, make sure to keep an eye on your inbox for those conversations that are going to come through. Again, you can respond directly to the email, or you can log into your Acelab account. It's a great way to get some additional questions answered directly from the LMX team. So definitely keep an eye out for that. But other than that, we appreciate everybody joining us, and thank you guys for the great presentation. We hope you all have a great rest of your day.
Thank you.